The last distribution we will talk about for discrete random variables is the Poisson distribution. The Poisson distribution is a special kind of distribution. It's a count distribution. It counts the number of changes that occur in continuous intervals of time or space. So it might count the number of defects you would expect to see on a production line over a 1 hour period, the number of customers that would arrive at a teller over a 15-minute interval or a 2-minute interval or a 25-minute interval, something along these lines. So a Poisson process with rate lambda, we'll denote that by P lambda. So we'll say that X follows a P lambda distribution if the number of changes that occur in non-overlapping intervals are independent, if the probability of exactly one change in a short interval of length, H, is approximately the same as lambda times H, and if the probability of two changes or more in a short enough interval is basically zero. What we're saying here is that changes cannot occur like two at the same time. They can't occur simultaneously. There's always going to be at least some potential interval of time between the changes, or some spatial distance between events. So two people cannot arrive at the teller at exactly the same. When you use these conditions, when you have an experiment that satisfies the properties, then the question that you have is, what's the number of changes? What's the probability that the number of changes would be 0, would be 1, would be 2 over some unit interval, right? There's going to be 1 hour periods or 1 days where you will not have a client. And there's going to be days where you have 4 clients. Days when you have 2, 3, 4, 5, 6, or what have you. What's the probability that you will actually see a specific number of events over the unit interval? And there's a way to show using the binomial distribution that the probability of seeing exactly X events is given by this formula. If you have a random variable that follows a Poisson process, the probability mass function of having 0 event, 1 event, 2 events, 3 events, 4 events, and so forth, you compute it using a specific function based on the parameter lambda. Lambda to the x times e to the minus lambda divided by x factorial. And if you're interested, you can try to figure out how you would get there from the binomial distribution, right? I mean, this is roughly speaking the binomial coefficient. This would be the probability of success, and this would be the probability of failure. And then you would be counting the number of failures and the number of successes, roughly speaking. Now, don't worry about the derivation here. I only care for you to know that if a variable follows a Poisson distribution, this expression here is the probability mass function. This is a special distribution. It is such that the expectation and the variance have exactly the same value. That's surprising that there is even such a distribution. There is one. It's the Poisson distribution. It's the only discrete, simple distribution that satisfies this condition. Let's look at some examples. We'll assume that traffic flow is modeled using a Poisson process. So we know, for instance, that the traffic flows through an intersection at 6 cars every minute on average. There's going to be minutes where you have more than 6 cars, and there's going to be minutes where you don't have any cars going through the intersection, but on average, 6 cars per minute. What's the probability that there would be no cars entering the intersection in a 30-second period? So now what we need to do is to write this rate here, 6 cars per minute, as a rate over the unit period, which we have defined as 30 seconds, right? Because that's the question that we want answered. Over a 30-second period, that becomes our unit period. So how many cars per 30 seconds do we have if we get on average 6 cars per minute? The answer is simple, it is 3. That number here is the rate over the unit interval, so lambda is this number. Here we need to compute the probability x being equal to 0. That is going to be, according to the PMF for the Poisson formula, 3 to the 0 times e to the minus 3 divided by, and here there's a typo in these notes, it should be 0 factorial. That's e to the minus 3 divided by 1, which gives you about 5%. So 5% of the time you would not see any cars go through the intersection, assuming that the number of cars going through the intersection is a Poisson count, and that there's on average 6 cars per minute going through the intersection. Now we'll look at another problem. Imagine a setup where you run a hospital, you're the administrator of a hospital, and you need to schedule night shifts in the maternity ward. We assume that there are 3,000 deliveries per year. Now if these deliveries happen randomly around the clock, then you would expect there to be 1,000 deliveries between midnight and 8 a.m., right? That covers a third of your day, and you'll have about a third of your deliveries during that shift, if the events happen randomly around the clock. Now, is this reasonable? It isn't, because in many instances, deliveries are induced, and they're induced when the physician is there with the mother. Now, in practice, if we make the assumption, though, that the deliveries occur randomly around the clock, a third of them occurring between midnight and 8 a.m. would be a time when much of the staff is not actually on duty. So you need to staff a night shift to allow the ward to cope with the workload on any particular night, or at the very least on a high proportion of the nights. If we agree that this is something which is modeled by a Poisson process, we would expect there to be, on average, every night, about 2.74 deliveries, right? There's 1,000 deliveries in total, on average, during the night shift, and there's 365.25 days in a year, roughly speaking, right? We're taking into account leap years here. If the number of deliveries does follow a Poisson process, then you can compute the probability of delivering 0 babies, 1 baby, 2 babies, and so forth. Here are some of the probabilities using a lambda of 2.74. There's about 6.5% chance that you will not have deliveries. There's about an 18% chance that you'll get exactly 1 delivery, 24% chance you'll get 2 deliveries, and so forth. Okay? Now let's say that the administration of the hospital, or at least the administration of the ward, wants to be ready for the greatest possible traffic on 80% of the time. So 80% of the time, we want to have as many staff as possible so that we can handle the worst possible case, the busiest situation. So how many deliveries should you expect? So you're looking for the value of x, which will make it so that the probability that you have fewer than x minus 1, including x minus 1, should be smaller than 80%, but that the probability of having fewer than x deliveries should be greater than 80%. Now, you can do this using R. In R, you would compute the cumulative distribution function using the Poisson function. 3 is the number here corresponding to x minus 1. 2.74 is the number corresponding to lambda, and you'll get that the probability of having 3 or fewer deliveries would be 70% or 70.5%, and the probability of having 4 and fewer deliveries is 85.7%. So if you prepare for 4 deliveries a night, you will be ready for the worst on at least 80% of the night. Like, you'll be ready on average closer to 85.7%, but at least 80% of the time you'll have the right number of staff in the ward. Now, we're not asking how many deliveries are expected nightly. That number is 2.74. That is the actual lambda. We're trying to find the number of deliveries we should expect on at least 80% of the night. Now, you could say, well, if I prepare for 5 deliveries, I'm still going to be ready for at least 80% of the nights. It's true, it's just that you're going to be ready also for like 90% or 95% of the nights. We'd have to compute Poisson 5 to 74. But the worst case scenario, if we want to be ready for at least 80% of the night, would be to be ready for 4 deliveries a night. This is what the PDF and the CMF for this distribution looks like, right? Notice here, we're even seeing it is likely, it's not 0, it's a little bit above 0. There's a probability that you would get 10 deliveries in the night, even though on average you'll get about 2.74. On average, this is the number of deliveries you get. You could get 10 deliveries. What we're saying is that for 4 deliveries, which corresponds to this line here, you have a line which crosses the CMF at, well, at least at 80%. It crosses at various locations, but the 80% line here would cross the CMF when x equals 4. How many nights in the year would you expect there to be 5 or more deliveries? Well, you need to compute the probability of there being 5 or more deliveries, this quantity, and you need to multiply that by the number of nights in a year, which we said was 365 and a quarter. Or, if you'd rather, the probability of there being 5 or more deliveries would be the same as 1 minus the probability of there being 4 or fewer deliveries. And this quantity you can compute in R using Poisson. You can also compute it directly, right? You can say what's the probability of x being smaller or equal to 4. That would be the probability of x being equal to 0, so no deliveries. Probability of having 1 delivery, 2 deliveries, 3 deliveries, 4 deliveries. And then each of these can actually be computed by replacing the value of x by 0, 1, 2, 3, and 4, right? So here you would have lambda to the 0 times e to the minus lambda divided by 0 factorial. And here you would have lambda to the 1. Let me just rewrite it here for this one, right? Lambda to the 1, e to the minus lambda times 1 factorial, and then probability of there being 2 deliveries, assuming a Poisson process, and assuming that these deliveries are happening randomly around the clock, which we think might not actually be reasonable, and so forth, all the way to x equals 4. Or as I said, you can compute the cumulative distribution function value for 2.74 in R using this function. So if you compute or evaluate this expression, you will get 52. So you would expect there to be, roughly speaking, 52 days in the year, 52 out of 365, where there would be 5 deliveries or more. And that amounts for about 20% of your year. Over the course of 1 year, what's the greatest number of deliveries that you might expect on any night? Where you're looking for a probability or a number of deliveries which would make it so that when you multiply it by the number of days in the year, that product should be greater than or equal to 1. You want to find the largest value of x for which this is going to be the case. The reason being, if that product is smaller than or equal to 1, you can't actually expect over the full year for that number of deliveries to have happened. The probability is just too small on any given day, right? Here's a bit of code in R that would allow you to find the x. I invite you to try to run the code on your machine and you'll find a number of x's. You'll find the one which is highest. That value is actually equal to 8.